Let us explore some more features of the graphical user interface. This time we are going to use the following connections. You can see the programmable voltage source is connected to in2, that is a 0 to 5 volt input. There is a capacitor connected to in1 and a resistor, a light dependent resistor to sen, and a piezo buzzer is connected to square 1. Microphone output is connected to A2 and the AC output, the sine output is to A1. First, let us see the effect of the programmable voltage source. Set it to 1 volt. Press enter key. It is set to 1 volt. Now, what is it in 1? It is the same value. Now we can assign in 1 to say channel 1 and make it say 1.5 volts. And again, if you go and measure in 2, it is same. Here you can see that the measurement accuracy of in1 and in2 are better than A1 and A2. So if your voltage to be measured is positive and from 0 to 5 volt range, use in1 or in2. Now if you want to measure the capacitance that is connected from here, you can see from in1 to ground, you just click here, measure capacitor on in1. It shows the value here. Only thing you have to remember is, while starting the program, you should not have the capacitor on the socket in1, because during startup the program measures the socket capacitance and stores it there. Now let us measure the LDR. Like the LDR is connected from sen to ground, the sensor input. Remember that this input sen is almost like in1 and in2, except that inside there is a pull-up resistor to 5 volts. That means this resistor and that 5.1 kilo ohm resistor acts as a potential divider. So if you measure this voltage, since the other end, this arm is known, the 5.1 kV know, we can calculate this using Ohm's law. So just click on measure R on sen, we are getting some value. Now I am illuminating this LDR from the light of a fluorescent lamp. A fluorescent tube is illuminating it. So if you measure again, you can see the value is changing. So it's better to assign it. See, when you see a variation like this, you assign that to a channel 1. This is one of the useful features of XPICE. Like a measurement, you can always plot a graph. So now change the time scale. You can see that clearly there is a oscillation. And to measure this frequency, drag this channel 1 to fit, and you see that the change is at 100 Hz, that is twice the line frequency. And if I remove this, take this box, and I'm going to just illuminate the LDR with daylight, say showing it to the window, you can see that it is losing that oscillations. And now coming back to the fluorescent tube light, it again appearing there. Now let us see how we can test the microphone feature. The microphone output is connected to A2 and the microphone is located here in this side, and we have the piezo buzzer sitting here. So we have to apply a square wave here on square 1, so that piezo will make some sound. So we can do that by sliding this, but before that let us assign channel A2 to channel 1. So this is a microphone output, there is nothing now. Now let us move the slider. So this frequency, you can see, you can measure the frequency here, that is same as the frequency you are setting here. So this is how you can capture sound using the built-in microphone. To put it off, just remove this now. The two square waves, square 1 and square 2, can be set to different frequencies like this. You can see square 1 is now set to 100 Hz, and I'm going to assign this square 1 to channel 1 because the readback is given to square 1. So square 1 is 100 Hz. You can see here. Let us change the volt per division to 5. Now make square 2 say 200 Hz. 200 and make square 2. Now to view square 2, move that to another channel. So now you have both of them. We can shift this a little bit. So you have both square 1 and square 2. It is also possible to assign both of them to the same frequency and control the phase difference between them. So we will remove this, both gone, and say click on both. Now both will be assigned to 200 Hz. You can see, but they are in phase. Now we'll go here, the delta phi in percentage, let us put it say 50%. That means they will be out of phase, 180 degree, 50% means. So remove this, put it again. Now you can see they are out of phase. When this is low, that is high, right? So you just see here they are totally out of phase. Now you can make them say 90 degree out of phase by putting it as 25%, put it off, put it again. So now if you look at that, you can see that this is rising and this is rising after 90 degree, where this is in the middle. So you can generate a waveform, two waveforms at the same frequency with whatever desired phase in between, and this thing can be used for studying logic gates. Suppose you give these traces to an AND gate and the output can be put back into another channel and seen where the resultant waveform. You can perform several experiments from this interface, but many of them require separate software. To access them, click on the experiments button. You will see a pop-up window, and from this list you can choose the required program and execute them. For example, I just choose a simple one like control PVS, and the pop-up window will bring it here. See, now just sliding this, I can change the value of PVS, but so long as you are inside this main window will just freeze. I mean, it will not operate. Once you quit this, the control will come back to this window again.